Good morning, everyone. Today, I'm going to be talking to you about an introduction to chemical equilibrium, or as I like to call it, an approach to study the extent of reversible reactions. Throughout class today, we're going to be touching on a couple of different concepts. The first is just, generally what is equilibrium and why is it important to all of the fundamentals that we're going to be studying throughout the semester. Then we're going to determine how do we determine whether a reaction is actually at equilibrium or not. Then we're going to spend some time writing out equilibrium constants so that we can determine mathematically the expressions for writing out whether a reaction is at equilibrium or not. And then lastly, we're going to think about how we can use the value of these equilibrium constants to determine whether a specific reaction will favor the products or the reactants. And by the end of class today, we should be able to, together, write out the equilibrium constant for the reaction of nitrogen gas and hydrogen gas to form ammonia gas in a reversible reaction. But before we get into the actual chemistry, let's talk about equilibrium in general in a macroscopic sense. When you look up the definition of equilibrium in the dictionary, you're going to get this: a state of balance between two opposing forces or actions. And when I like to think about things that are, opposing forces that are equal and opposite, I like to think about a seesaw with two equal weights on either side. You take the seesaw, you place two of the equivalent weights on either side, and the seesaw will balance itself, indicating that those forces are equal and opposite, and it's not tilting in one direction or the other. If you were to bring this out of equilibrium and change the weights of these two circular weights here, you would get something out of equilibrium, and that seesaw would begin to tip as one of the circular weights is significantly heavier than the other. Your masses are now no longer at equilibrium, so you're no longer balancing those forces equal and opposite. And if you want to again get back to equilibrium, you have to change the weights of those two circular weights in order to get back to that equilibrium where the forces are equal and opposite. In a chemical sense, when we think about equilibrium, we think about the position of a chemical reaction in which it comes to an apparent end and is a mixture of products and reactants. So that means that the forward and reverse reactions are going at the same rate. And let's think about a general chemical reaction, just the reaction of reactants A and B to form products C and D. And just to orient you a little bit on the nomenclature here, the uppercase letters indicate the actual molecules that you're putting into the reaction. The lowercase letters indicate the stoichiometry. And the fact that I am using an arrow that goes in both directions indicates that this reaction is indeed reversible. So when you think about a reaction going to equilibrium, let's say I put reactants A and B in solution and I let them react. They should form some amount of products C and D over time, and then that reaction should stabilize and the forward and reverse rates should be the same. If we were to look at a plot of concentration versus time in this regard, it would look a little something like this. At the very beginning of the reaction, you would start with 100% of your concentration being your reactants, which is the red line, and 0% being your products. As the reaction goes, you would see a growth in the concentration of your products and a decrease in the concentration of your reactants until you reach a point where the concentrations level off and the apparent forward and reverse rates are the same. And that is what we call equilibrium. That's inside of this gray box where the concentrations are no longer changing and the forward and reverse reactions are at the same rate. Notice that this specific equilibrium is not at a 50-50 mixture of the products and the reactants. That doesn't necessarily indicate equilibrium if you're at a 50-50 mixture. Equilibrium can be obtained at any mixture of both products and reactants. So we've thought about what chemical equilibrium is. How do we determine whether a reaction is at chemical equilibrium or not? So thinking about the same reaction, A and B going to C and D, what are some of the key things that we think about when determining equilibrium? One, there's no macroscopic evidence of change. There's no color change. There's no change in concentration of your products or your reactants. There's no viscosity change or temperature change or anything that would indicate the reaction is not yet at equilibrium and not the forward and reverse reactions are not the same. Two, the equilibrium is reached through a spontaneous process. So if you add the reactants to your mixture, it immediately starts to form products without any added driving force, be it temperature or catalyst or anything of the sort. 3, the forward and reverse reactions show a dynamic balance. So let's say you've let this reaction get to equilibrium, and then you add more of the reactants. That if you add more of the reactants, then the reaction will then go back to equilibrium. So it's a dynamic process. It's not just it gets to equilibrium and it stays there. And lastly, the equilibrium state is the same no matter the direction that you approach from. So if you start with just products or just reactants, or a mixture of both products and reactants, you will end up at the same equilibrium state. And so now we've talked about some of the ways that we can look at these chemical equilibrium reactions and go from there. Let's think about how we can mathematically determine equilibrium states. So thinking about this reaction of the products, or the reactants A and B, going to reactants C and D, how are we going to determine mathematically what this equilibrium constant is? And to denote the equilibrium constant, we just say K EQ as we're using it to denote our equilibrium constant. So as shown previously by many experiments and the law of mass action, it was experimentally determined that for any specific reaction conditions, so any specific concentration, temperature, things like that, as long as the reaction conditions were consistent, no matter what ratio of products and reactants you started at equilibrium, you would always end up with the same ratio of products and reactants at equilibrium. So that ratio is determined by the concentration of the products over the concentration of the reactants. And just to show you, your uppercase letters are in the concentration and your stoichiometry is the exponent. So this was determined that at equilibrium, the ratio of your products to reactants would always be the same or nearly the same. So let's think about this. If we have a KEQ that is much, much greater than 1, how would we determine whether this reaction is going to favor products or reactants? So let's take a moment and think here. We have our products as our numerator, our reactants as our denominator. If this ratio, or this fraction, is much, much larger than 1, we would expect the products to be significantly more than the reactants, right? Because if this is a very large number and this is a very small number, it would be much, much greater than 1. And then vice versa, if KEQ is much, much less than 1. It's a more interesting case, or an interesting case, if your KEQ is about 1. Because what that means is that you have a mixture of your products and reactants. So it's not really significantly favoring one over the other. OK. So now let's go back to that reaction that we talked about from the beginning of class. Now, instead, we're going to be thinking of the reaction of nitrogen gas and hydrogen gas to form ammonia gas. How would we write out the equilibrium constant for this? If you take your KEQ here, and you remember that the equilibrium constants are concentrations of products, so your ammonia to the second power because of stoichiometry, over your reactants, which is your concentration of N2, and your concentration of H2 to the third power because of your stoichiometry. This is how you would determine the equilibrium constant. And lastly, if this value was significantly larger than 1, we would expect what to occur? Right, we would expect the products to be significantly favored over the reactants. OK, that's all the time we have for today. Thank you all very much for your attention. Next time in class, we're going to be learning about how if we change partial pressures of the gases, or if we change temperature, how that will impact the reactivity. Thanks.